Today, we're going to talk about UNet, convolutional network for biomedical image segmentation. This paper in a medical imaging journal, not in the premier computer vision conferences, but yet this paper becomes such an important historical piece of the evolution of deep learning in the computer vision because it is one of the first models, probably the first model to figure out a way you could take image as an input and put out another image as an output while running convolution along the way. And if you see this structure, you can start to recognize a few familiar features. So the first feature I would like to highlight is that we have input image and it's visualized in this way with higher resolution, but eventually throughout some processes, a sequence of convolution and max pool, and you get lower down to much smaller dimension. And this is like a triangle, and it'll tell you this is an encoder architecture. On the other end, you have an opposite direction going from very small dimension to large dimension for your output, which is the image. And this is a decoder. In the middle, this is a bottleneck shape. So these are code that the hope is that encoder somehow manages to capture the most essential important information in your input image. And the decoder can take those and generate an output that you want. And the new feature that we have to learn today is this horizontal arrows. What are these arrows doing here? Another new thing is you have these up arrows. And what are they? Horizontal arrows are operation called concatenation. So concat. And to put that into perspective, in the previous lecture, we talked about residual network and see addition of features coming from upper layer of your network to a lower layer of your network. And the upper arrow we're going to learn today, this is the process of transpose, called transposed convolution. You can think of it is the opposite direction of a convolution. If you run convolution in max pool, you reduce the dimensionality of your feature map, and transposed convolution is supposed to go in the opposite direction to increase the dimensionality or increase resolution of your feature map. And that's what underlies the process of decoder. You're going to go from code, very small, to decoder, which is large. In this case, for the output for this particular application is to output a segmentation mask, which is the image. And input is going to be an image as well, a medical image. Okay. And we're going to look at the calculation today, and we have to if it looks like a U shape, that's where the name U comes from. So this looks like a encoder decoder with U shape. And we're going to turn that 90-degree in this way. So we'll see how the calculation can kind of go down in this direction in my next tab in the Excel sheet. Also, I would like to kind of squeeze it to realign this so it goes to the vertical direction in the stack. Let's go to the blank sheet. First, I would like to talk about the first operation that is a concatenation. What does this horizontal arrow do? I would like to consider the network, in this case, a very simple multi-layer perceptron. We are in the fully connected layers in each layer is a fully connected layer. A quick overview of what this architecture does. We're going to take four features, one, two, three, four dimensions, and we run a 4 to 4 linear transform and activation function ReLU, another 4 to 4 transform. So what this not encoder in the sense that it's not reducing the dimensionality, but I will use this network to illustrate concat operation. So now we have 4 on the ReLU, and concatenation basically going to bring input from up in your network, earlier part of your network, and then bring it down here. So we are doing it by hand. What I need to do is that maybe just what I will do is I will just maybe hide this so I can actually see together closer. So hide all this for now. Okay. And then what I would like it to do is that I will bring it down here basically a copy down here, 2, 1, 9. Actually, this is a very strange color. Let's do this. 2, 1, 9, 4. That's what I like to accomplish. Bring this feature down here as a copy or references of the same features from up in the stack. And then, so if I were implement it using code, I will basically just do equal sign and now select this. Okay, so I have this. All right. Now we're going to open it up. Then you'll see the result of concatenation. Open this out again. So the result of concatenation is that instead of having just 4 dimension in this output, all of a sudden, because I concat, I get 8 dimension, 4 to 8. So this is a whole tensor or 2 matrices combined together. And we would like to apply linear transform to this. All of a sudden, I need more weight. So I have this 4 biases here already. I want this to go from 8 back to 4. And this is my output dimension. What will be the size of the matrix I need? I'm going to need, this size kind of easy, 4. And then the other side must be 8. So I can match one of these 8 dimensions. So I'm going to draw a location 1, 2, 3, 4, 5, 1, 2, 3. So this 8, I think it's about here. So this will be my 8, 4 by 8 matrix of weights. So I can use rand array and to give me those weights 4 by 8, 4 rows and 8 columns. And when I fill this weight, this matrix multiplication right here will just work to make this as matrix multiplication here and pass through ReLU. Okay, so this is how I would concat features across layers, and they will achieve the effect of having the skip connection and being able to mix logic across multiple orders. And so in the previous lecture, we look at addition, and in this case, we look at concatenation. And the difference would be the size of your linear layer transformation. All the weight matrix will have to go up in size in order to accommodate more features in the result concatenation. And so what if we need to concat different dimensions? It's the problem we're going to look at. So in the earlier example, we look at concatenating 4 and 4, we get 8. This seems to be easy. In this case, I have the transform go from 4 to 4 for my first layer. But for my second layer, I'm going from 4 to 6. And now I have 6. I would like to concatenate 4, and it seems very straightforward. Basically, I just concat and add this 4 at the end, I get 10 dimension altogether. Okay, so in this case, I just have to have a larger weight matrix here. So what will be the dimensionality of this weight matrix? What is the shape of this weight matrix? So here is 4, very easy. My output is 4. But here I would like to have 6 by 6, 10 columns here. So the first 4, I'm going to draw like this one. This 4 is going to somehow map to combine with this 4 through a linear combination. And this 1, 2, 3, 4, 5, 6. So this is how I will visually match to get their sizes to match. So this is what I need. So it's going to be 16 altogether here, right? No, not 16, 10. 6 by 6 and 4, which is 10. So this here, I'm going to write rand array and 4 rows and 10 columns. They'll give me the weight matrix I need to perform linear transformation. So concatenation implies that you have to add more weights in order to perform the same linear layer. But you also have advantage of mixing features from across multiple layers. So how is it different from addition, which is what we looked at in the residual network? So this is to serve as a quick review. So when we have addition instead of concatenation, so you don't see those extra rows. Instead, you get, let me just hide this so you can see them closer. So I'm bringing this same shape, 4 by 3 and 4 by 3. So what I want to do is that I want to rewrite f of x. And then this is there will be x coming from here, my input. So I like this to be add together, somehow add together. If I add them, they'll give me f of x plus x. And I'd like this to be ReLU activation function applied to f of x plus. And then we learned this last lecture is called residual. And this is x is my input earlier on. So let's implement this. Or I can actually do it by, this is trying to do it by hand for a couple cell. For this one, I'm gonna get 2 by 2, 2 plus 2 and ReLU, and it's going to be 4. For ReLU for positive values is just gonna be the same number. And this is when things become trickier. 1 plus minus 2, you get minus 1. But with ReLU, I want to get 0. That's what I want to do, okay? I just completed 2 cells to practice. I'm going to implement this. I have ReLU, I have a function ReLU. So I'm going to select my x and plus f of x is here, f of x, and then it will be the simple implementation. So if I hide real quick, you'll see 4 and 0. They match my hand calculation results earlier. So this is, and then continue here for linear layer. So instead of this much wider weight matrix, what will be the size I need? I need 4, and since 4, this had to match, okay? 4 by 4. So for 4 by 4, I'll do ren array 4 and 4, and then we'll implement this weight matrix and to complete this addition. Okay, so all right. And what happened? We need to add different dimensions. In the concatenation example, we just put them together. We don't even check whether the dimensions are the same or not. But for addition, the dimension have to match. Remember, we were trying to add the yellow to green, but their shape don't match. You just cannot do that. And so in fact, I'd like to do is, so here is a skip projection in that I could first project X into a dimension that will be the same as the dimensionality of the feature down there. I would like to combine together. So in this case, I want to go from 4 to how many numbers? 1, 2, 3, 4, 5, 6. It's 6, right? So it's 6, 4. So I need to project to 6. And the size of this matrix for projecting that is going to be 4 by 6. Sorry, 6 by 4. 6 by 4. Okay, so I'm going to use ren array again. Ren array. And then how many rows? 6. How many column? 4. And then this will be my weight matrix. And for this one, it will be matrix multiplication of my first one is actually, I will select the weight and biases, and then I'll select the input coming from the skip connection, including the actual rows of 1, and there will be the projected version of the X. Now they have the same shape. Now I'll be able to implement my ReLU, and fx is this one, and x is going to be over here. Now they're the same shape, you can add them together. It said it doesn't work. Let me just check my result. It's, oh, because I didn't add a plus sign, there should be plus here. Add them together. Then this is correct. Let me fix this. Format. Okay, so what I just did is to show you how we will add dimension, add features across layers. In this case, it's not exactly what the residual network looked like because in the real residual network, we will at least skip 2 layers, but in this case, it just skip itself. So for the sake of simplicity, my goal is to illustrate the difference between an add and concatenation. There are 2 different ways to bring features across the layer from something from the top to somewhere in the bottom. Okay, so that is where, let's go back to this tab. This is what this horizontal yellow arrow does to be able to bring features from here and to here. In UNet, we use concatenation. In residual network, we use addition. They have different implication in terms of the number of weights you need for your next linear layer, also whether they should match in dimensionalities. Now we're going to talk about UNet, the encoder and decoder architecture part of the UNet. But to understand that, you don't really have to use convolution because the concept of UNet is applicable for MLP as well. And so we'll use MLP to help you gain intuition of how the encoder decoder are put together and how the concatenation works to bring features across layers. So first, a quick overview. We're going to look at encoder, and afterward, keep going down. We're going to see code. And then the next section, we're going to talk about decoder to reverse the process. All right. So there's a plan. Let's go back up to the beginning of the encoder of the stack. So what I want to do is to focus on the change in dimensionality and also operation. And so first, I have 8 is my input. And when I apply the first transformation, this is a linear layer. And for in a convolution case, which is going to be convolution, but this is a linear layer, fully connected network, go to 8, 8 to 8, and then we have ReLU. Okay, and then you can see that it's going to follow a kind of skip connection, and it's going to be concatenated with something else down here. We're gonna see later in the decoded part. And after that, and we have a layer that we're going to reduce from 8 to 4. You can visually see there's a reduction in dimensionality. So we need a weight matrix to do from 8 to 4. So we already know it's going to be 4 by 8. That's here 1, 2, 3, 4, 5, 6, 7, 8. I mean 4 by 8. Okay. So we're going to do rain array 4 by 8 and to implement this weight. And then 8. Okay, and then we'll have this. And this is hard to see. So what should I do? How can I fix this? I just going to go to here and just change this. Okay, it's easier to see by weight. And then we have a ReLU here, activation. And then we'll do just regular transform, a square matrix to get the same dimension back. And here I'm ready and have another ReLU. And I'm ready to pass it down again through a skip connection, a shortcut down there. And I intend to concat later, okay? And then so here, there's a downsampling, a reduction in dimensionality to 2. If we see that, I know I need a 4 to 2 matrix, which is 2 by 4 in terms of its shape. So I'm gonna do with 2 by 4, I'm just gonna type it quicker. I just say to 1, 0, 0, I just randomly assign some 1 there. Okay, and maybe add another bias here just for fun. Okay, so I have another reduction in dimensionality. Now these are encoded. You can see that channeling down the downward triangle effect. We're getting from 8 to 2 down. So, and then we might just apply, in this case, a activation function, and that will do another transform, linear transform. This is 2 by 2. So we'll get the same dimension back as 2 to 2. And then with another ReLU activation. Okay. I realize it's not a great location. Then move over here, more middle of the screen. And then we'll eventually do another convolution, another transformation here, another ReLU here. Eventually, then we stop here. And this is low dimension for 3 input examples. I'm going to call it code. That's where our bottleneck is. All right. So up to this point, other than the promises that I'm going to have a skip connection down there to concat, this process just looks like a normal encoder in the autoencoder that we looked at in the previous week. Okay. So the next section, we're going to talk about the reverse process of decoding. How can we then decode from this code using following decoder while being able to take features from above? So first, I would like to go from a low dimension to higher dimension of 4. So in this case, in fully connected network, all we have to do is just specify the right size for my weight matrix in the fully connected case. So what we need to do is I need 4x2 matrix, which is, I put it right here, RAM array. And later on, we're going to look at the convolution network case. So we're gonna see transposed convolution to accomplish this. And this now finally we see that the concatenated feature flow down here and being put it over here. And as a result, we go from 4 to 8 dimension because this altogether this is 8. Okay. Okay, and then for this, if we would like to apply linear transform, then we'll have a larger 8 to 4 transformation because I want to back to 4 here again. In this case, I will need a 4 by 8. Maybe just I will use my color pencil to just draw them out. So easier for me to know where I should put my weight matrices. So we'll have first block and second block the weight. They match the different parts. So this is what we computed from the previous layer. And this is where the UNet architecture brings in through this concatenation, skip connection from the layers above. And then altogether, we need this much weight. 4 rows and 8 columns. Once we have that, it will be able to perform this linear transform. And then we continue the process with value. Okay, and then we have a regular linear transform, linear layer here. 4 to 4 is a square matrix with weights, and we have another value. And I think I just do another transform again. Okay, and square matrix and value in this case, we're not seeing anything special, except once we get to this point, we like to do an upsample here to increase the dimension to 8. And so this one things is slightly thing to think about. So we need this 4, 4, and 8, 8 over here. So this is how many weights I need. So now I can implement this range array 8 by 4, and then we'll accomplish this upscaling from 4 to 8 using a fully connected network. Again, in the convolutional network case, we're going to use a transposed convolution to accomplish this. And once we bring back to the 8, and then we'll go back up to bring down the features, and I'd like it to be also 8 as well for 8 dimensions. So in this case, it's 8. And so, and eventually, because I bring more features from down there, we'll go from 8 to 16. Okay, so 2, and then for my linear layer that immediately follows, well, then we need 8 here, and we need 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This many weight. Okay, so I can put it here. I believe this is the right place to do range array, and then for 8 rows and 16 columns. And once say the weights right, we get this large, really large weight matrices, but we're able to bring the dimension back to 8 again, and we'll do another value. And then we'll do a regular linear transform, a square matrix 8 by 8 to keep dimensionality to 8, and do another value. Okay, and eventually we're done. This is the result of decoder. We get back to the same shape as our input in this case, but it doesn't have to be. It could be a smaller map in the case of the smaller segmentation map. But the bottom line is that we're going through the encoder-decoder process in the multi-layer perceptual architecture without resorting to convolution yet. But you get to see the effect of concatenation skip connection here. What I'm going to do is I'm going to zoom out to maybe 50% so you can see to review the process we just did. Then go back all the way up to the encoder, going down the encoder, and then eventually we hit our code, and then going back up the resolution and get back to the original resolution, except with this arrow to connect them together, okay? For the concatenation here. And each time with concatenation, the weight just grow to the left, more weights in order to accommodate the feature you are bringing in from up in the network. Now we're going to move to the convolution case, okay? Now we're going to talk about in the convolution network case, when we're dealing with 2D images or with sliding window and so on, how can we perform the upscaling process? Earlier, we simply apply a fully connected network, a large matrix for you to multiply. And here we like to use this upscaling that if we have this, imagine we have a low resolution feature map 1011. In the fully connected layer case, we're just gonna flatten it to 1101 and just apply a large weight matrix to convert them into something bigger, like this is supposed to look like. So this is in the fully connected network case, we're gonna just convert them into something bigger. And in this case, I would like this feature map to be filled with this pattern. This is one pattern as an example. This is a filter. So in this case, this pattern looks like this: 1 1 and 1 0 1 1. And what I like to do is for every one, I want to get 1011, 1011, 1011. For zero, it's just going to be 0 0 0 0 0. And to do that, what I have to do is that suppose for each P in F, I would like to simply do element-wise to the kernel, in this case, element-wide multiplication with the kernel. So what I would do is I would just do take this and times and my entire kernel. So we'll implement in this area. So we do the same thing here. I'm going to select my low resolution value, but I'm going to do element-wise multiplication to this one. Okay, and to do the same thing. So I'm basically simulating a loop iterative process to do that for each cell. And I can add, without add, I'm just going to perform element multiplication. So now I have this, except this one doesn't look, oh, this not look correct. This is supposed to be, let me redo this one. So this cell is supposed to be, I take the value here and element-wise broadcast to the pattern of here. So this is what I just accomplished the similar, this upscaling I just did here. And you could, to prove that this kind of work, you can just play with it, just change the pattern. You can see that I just update the pattern, okay? And if you change my lower resolution feature map to something like this, so you could also see that the rendering effect is kind of just updated in real time, okay? So that's what I'll call parametric upscaling. When you just upscale, you have some parameters you learn for this pattern to control. Given a signal in a low resolution feature map, how you like to render into a high resolution to represent a signal. That's the principle behind this. And next, I want to talk about the operation transposed convolution. In order to take advantage of a GPU, you would like to re-express for the iterative process I just went through maximum multiplication. It turns out it's going to be the transpose of the convolution process. And so what happened here is that in the regular convolution, you might remember we'll do an image to column, but in this case, it's transpose, it's image to row. So we can turn this into a row 0, 1, 1, 1. And for the kernel or the filter here, instead of converting into rows, we convert it into column in a transposed manner. So in this case, 1011 becomes 1011. And then we'll do matrix multiplication and then reverse this process from column to image. So it used to be image to column, but now we're gonna do the reverse process. So we're gonna do column to image. This column will become this image, okay? But let's just implement some of this real quick. So for image to row, I'm just going to do to row and take my input feature map over here. So I put my value over here, 0, 1, 1. This is also similar. I'm gonna do to column and then select this. Okay, and now I have this implemented. And this is probably the most magical part for, and if you work out the math, you can do maximum multiplication to take the result of this and take the result of that for your input and multiply them, you get this, the windows that you do if you would run sliding window on your upscale higher resolution image, super resolution image, you will get these windows. So then I can reformat them back to the window here. So what I will do is that it's going to be wrap rows, wrap this thing back into the window of 2x2 window. So then we'll repeat this process of here. I just copy and paste, but I'm going to adjust my window a little bit to make sure I'm selecting the right window. So this should be this window, okay? And then this one, where the copy here. Sorry, copy and paste. Now to make sure this is actually this window. And this the last one is here. And this is this window, okay? So what we just managed to accomplish is we have something similar to what I had earlier. They will have a feature map to control how I want to render each individual location into higher resolution. So we can just play with it a little bit to just prove that this actually works. So I moved the feature map a little bit to 1101. So we have the pattern of 1101 correspond to the pattern, parametric pattern we learned here. So we change the pattern here, the pattern changes accordingly as well. All right. So that is the principle behind transposed convolution. Whatever we used to do in rows, that we do in columns. Whatever we did in column, we do in rows here with respect to convolution. So next, let's look at the extended version of transposed convolution. What if we have multiple feature map? So for each feature map, what we'd like to do is that there will be a different pattern and we can render for each feature map. So since I have three, so we want to have three different patterns. Each feature map will describe. So for instance, if we have the first feature map and this particular location is 1, so we'd like it to render the first pattern here. And the other thing will be just 0. And for my second feature map, if we got every time we see the 1, we want to render the second pattern. And for third feature map, similarly, for location 1, we want to render this pattern. So that's what we do. And I can also output 2 higher resolution rendering of my feature map. So in this case, I use blue to denote that. So suppose for my blue, I have another feature map in my output. Later down here, I actually prepare this location, okay? My second output feature map, I would like to render with a different set of vocabulary. And then this use blue here. So here, if I have 1, I want to render this guy. So there will be 1, 0, 0, 0 here. And if I see 1 here, I want to render the second vocabulary. It looks like this. So where's are my 1s? It's going to be here. 0, 1, 0, 0. And my third vocabulary would be the same process. I'm going to put 0, 0, 0, 1 over here. So that's my goal. I like this feature map to be combined and in this one. Okay. And then this one, blue one is going to be here. It's actually green. It's just blue. Blue is going to be my second output, higher resolution feature map here. So over here, okay. So this is my goal, all right? So all I have to do is just follow the similar principle of, I was just gonna two row, and take my first one, and repeat the same process 2 times, but make sure I'm selecting the right feature map here, okay? Okay, and then while I'm doing this, maybe I should hide my ink so easier to see my code. Hide ink. Okay, and then for 2 image column, we'll do similar process, 2 column, image to column to turn my pattern into this way. I'm gonna copy them over, but let's make sure I move so that they map to the right map. Okay, here. And I repeat this for blue one. So I'm gonna do blue one, it's gonna map them 1 by 1. Enter, and this one is going to map this one here, actually here. And this one going to map here. And now I have the column kind of off, then fix a little bit. I'm going to copy my shape here, my format here to fix this. Okay, so I have distinct kind of red, brownish part and also blue part. And once I map this out, to perform this super resolution scaling become a very simple maximum application. It's difficult for CPU, but very simple for GPU. And then once you put all this tensor into your GPU's memory, and you get very fast rendering effect. And done. And then you just have to rearrange them back here. So what I'd like to do is I would like to take this and put it into this. Let me just remove this now. So I take this window, fix it here, and take this window, fit it here. Take this window, fix this here, and take this window, fix this here. I think I already finished this two window. I just gonna do this one. So red rows, and then take this window and then red by 2. So I'm done. Okay. Okay. And now I'm going to do a similar red rows, and then take my second window over here over 2. Then I finish this one. And then for my next one, I didn't delete the code. So for this one, I'm gonna do is select this window. Actually, no, let me just do a red rows and select this window and 2. Okay. And then what we'll do is select this second window and then forgot to add 2 by 2. Okay. Now we just reverse the process of image to column and what did column to image and to accomplish this transposed convolution. Guys, trying to hide here a little bit to bring these two together. You can see the one I just kind of simulated with my handwriting 1100 does match this pattern here. And 101, this portion kind of match here as well, as you can see. And this corner matches here. So this is actually working correctly. And this all kind of live. You just change anything, you will get the result, rendering result updated. I'm just gonna open this to restore where we are. Okay. And next, I think it would be worthwhile to just review the convolution real quick so you can actually see the difference. The convolution is we start with high resolution image 4x4 here, and then we'll do the image to column. Okay. And then once we have that, we want to match a particular filter, and the filter will go through the process of flattening into a row. And so this could be linearly combined. And we repeat the same thing for the second channel. And then eventually we do the maximum application, which is a dot product, and get this value. And then we can just roll to image to back to our feature map here. And if you typically will also add ReLU. I just didn't have it here, but you can have a ReLU here for activation. Okay, so you can see that if you compare this one with the previous section, where you have image to column, in the transpose convolution, you have image to row. So it's like things that got transposed. Hopefully, this is a visual way for you to understand the underlying math. So lastly, I would like to finally go through the convolution unit, but because I have taken my time to go through the concat skip connection and also the process of transposed convolution. So in this case, we could potentially go a lot faster and to show how we can see all that in the convolution case. All right, so let's start with the first step of image to column. We have this 9 then we are running a 3x3 window, which was what we did here. So with a 3x3 window, we get to the column. This column will map to my first feature. We only have one channel, so channel go this way, and this get flattened into row, and this get multiplied into this cell, and we can they have 2 output channel, and then we'll repeat the same process. And then this get redo over here, and then good reformatted the image here. So it's kind of just trace this, okay? And then eventually, when you have 2 output channel, and then we will do is that we'll run another window. What is the size of the window here? I can see there are 9 here. So the size of the window, and now is like 3x3 here. So this become this window. Similarly, we'll do another convolution again. So this time map to here, And the second channel will map, if we have a second channel here, will map to this one. And this get mapped to this row. And this get mapped to this row. And then when we multiply them, we get another one. So this what I'm doing right now is a visual tracing of how convolution typically works in this case. And then we have ReLU to get this one and this one back to the image. And I have this arrow down here, we're going to concatenate with somebody else down in the decoder stack. So we have 3 feature map now because we have 3 sets of this convolution filters. Okay, and then we keep doing this. Now we are running sliding window again. This case is 4, so we know it's a 2 by 2 window. So they go back up. So this 2 by 2 window will be mapped, reshape into this form, and we have 3 of this because we have 3 channels. In this case, I do not see any weights here because I'm doing max pool. So max pool, this map to this map to this, and this map to this, and reduce into just one element, which is the maximum value in that response, and then reshape back into a feature map so we can continue. All right. So, and then this one back to here is a 2 by 2 window here. Okay. And repeat the same process with 3 of this. And then we'll map to 3 set of weights. And all this weight will be reshaped into this. Okay. All right. And then with that, we can actually multiply this. And then I will do a ReLU to get this and reshape into this. And so far, it's still very typical convolution processes. And we just keep, every time we apply max pool, we reduce the dimensionalities of the resolution. So we can have a skip connection down here. And this time, we're going to do another 2 by 2 window. Let's see what kind of operation we're trying to apply. It turns out we're going to apply max pool. So we have this 1 to 1 to 1 sort of the mapping, okay, with no weights to the left. And then eventually this become the first pixel of each of the feature map. It repeat that use matching multiplication to do it in parallel. Eventually, almost there, we have one more convolution layer. In this case, I use the entire thing as my window, okay? And then this is going to combine with this set of weights, and this set of weight is becoming a horizontal again. So you could match them, and to compute matching multiplication, and you ReLU again, and then eventually you have your first pixel of this final output feature map. In this case, it's small enough to 2 by 2 compared to the input image of 8 by 8. And then we can call it code. So this is the final output of the encoder, okay? And next, I'm going to finish up with convolution neural net on the decoder stack. So once we have a decoder stack, and the first is that we take the code, we like to bring up the scale it up by applying transposed convolution. So for transposed convolution, we'll take this image and then turn into a row, which is opposite operation. So once we have this row, so for corresponding patterns, we turn it into column as well. Turn it into columns, okay? 2 columns here. And once we have that, this convolution is going to be a matching multiplication. So we get this whole thing. And then each columns actually correspond to a larger, expanded version of the single pixel into a 2 by 2 window. So, and then we repeat this for this window, and repeat this for this window, and repeat this for the last window. And then we're reversing the process of sliding window in this direction. But as a result, we have an scaled up image, upsample image, or super resolution image. And this is coming from up there. We finally see the skip connection. So these are the 3 features coming from above. So we're gonna scroll up here, you can see, follow this arrow. So these are the copy or reference to the same image, but usually a copy because you might have to copy this tensor from the main memory into your GPU. Once you have this matrix out here, and you'll be able to convert into this large matrix format. So it will be here, this window. What is it? What do I have? This window back to this column format. And we'll repeat that for the other three channels. And this three channel actually came from above. And because now we have this, all this together, instead of 4, we have 12. And this map to this much larger matrix right now for convolution. And they are all flattened into this shape. Okay, and then we get the matrix multiplication again to get this value and get redo and then get this value as well, and do this 3 times for 3 channels. So this is the result of first convolution applied to a concatenation of your features, and also a feature that bring through skip connection. Okay, and then we continue this process for upsampling. Then we can see another transposed convolution coming up here. So we take entire image and turn it into rows here. Turn this into row and do the same thing for second image. Do the same thing for third channel feature image, feature map. That's what I mean. And then we do the same thing for this image pattern to generate. And then we do a matrix modification and do some rearrangement. We get back to this high resolution image. And we have 2 channels here because we have 2 sets of these patterns here. Red, kind of reddish, and also the bluish here, okay? Now 2 channels. Now I'm concatenate this with the feature from above. How many did we bring up? We brought 3 features, 3 feature map from above earlier on. So just scroll up a little bit, check real quick. So these are the 3 big features we just bring down, right? So okay, altogether we have 5 channels. With these 5 channels, 5 feature map. And we also run a larger window size. There's 3 by 3 window here this time. So 3 by 3 windows. This 3 by 3 window will give us this 9, a column of 9. And we'll do 5 of this. It becomes kind of big. Now we have this window. That's where it's supposed to map. And eventually we turn it into a row. It's too long, so I actually shift it here, over here. But the bottom line is that eventually you also multiply them to get this convolution. So we're still convolution, get this, and then we redo, get this, and then we reformat into this image, okay? And then do that for entire matrix feature map through matrix multiplication in parallel in a GPU. And then we could also continue to perform convolution. Now we have back to 3 channels. Then we'll convert, this analyze the first window 3 by 3 here. Okay, so that window. Then to run convolution, we also need convolution layer. It turns out this is actually my final convolution layer to get my final output. So I only have 1 channel because I want to get segmentation mask. Is only a binary of just 1 feature map for my segmentation mask. In this case, I flatten this up and I can do the convolution by matrix multiplication and get this value. And this value is kind of big, so I can apply the batch norm with mean and standard deviation to center this, and also use gamma and beta to rescale this and with an offset. And this is shaded to remind yourself that these are learnable parameters, gamma and beta, but the mean and standard deviation are calculated. Eventually, I then get a probability map. So I just get a sigmoid function to turn it into probability value. And then we turn that back to the image. So this is my output, first value, but we do that in parallel for all the other location, okay? All right, so this is the end of my attempt to trace through the UNet. And then if we can zoom back out now, let's select this. And zoom back out, you can see that we just managed to trace the UNet. Now, this is my decoder process. And then this is my encoder process. If I zoom further back out, and I hope you can actually see the U shape. So I'm gonna zoom to 10%. Okay. And then, and you'll see that finally you get to see the U here. U, but actually, rotated version of U. It's more like CNet, but it's the UNet. Okay. I hope that you can follow most of it. This is UNet, and it definitely encapsulates a lot of concept we have learned up to this point.